Okay, so start recording now. Right, so now we are going to discuss the topic of IP routing, right? So let's start it. So just take note, if you have questions, just speak through it because apparently the controls of the chat aren't visible when I do a share screen, okay? So just let me know. Okay, so here you go. Let's close this. So now we're in week number 5. So I think we're already past midway through the sem. So congratulations to you guys. So week number 5, we're going to cover the topic of basic IP routing and advanced IP routing. So hopefully the lecture for today will be a bit short, but it's a bit challenging topic. This is one of those harder topics during the semester. Next week and the following week will be more application technology, so there's less computation. So it should be less challenging as well. Okay, so let's go to our topic for today, which is basic IP routing, right? So last week we discussed one of the key aspects of a layer 3 network, which is IP addressing or logical addressing. So the layer 3 portion of the network handles both addressing and routing. We will today discuss the other half, which is basically routing. Okay, so what is routing? So routing is the process of moving packets from one network to another. The reason why this is important is because you can't make everybody just part of the same network, because you do want to impose things like policies, who's required to access what and all of that, right? So that's the reason why we created routing, because you have to subnet the network, then you have to allow certain things to pass through these networks. It is generally a layer 3 operation, so it's part of your IP stack. And networks can be of different protocols. It just so happens that today we're going to be discussing IP routing, which is part of the TCP/IP family of protocols. Now, routing is something, especially layer 3 routing, is something that you define. And the reason why this particular part of the lecture is a bit longer, or sorry, not longer, but it's a little more, it's a little harder, is because you yourself as human beings are the ones that actually set the route. Unlike switches, diba, switches also have a quote-unquote routing table inside the switch whenever it sees a packet. But if you notice from our lab 2 exercise, the switch is the one that adds it to that table itself. If you notice the source code of that mininet switch side emulator that you used in the lab exercise, you will notice that there is a hash, there is a dictionary that's created that effectively is your routing table. But it is automatically created for you, as opposed to today, it's something that we configure ourselves, okay? So IP routing can be described as what we call hot potato routing. So what happens when you get your hands on a hot potato? So of course, if it's hot, you pass it on to the next person. Whether you are sure or not that potato will get to its destination, you simply pass it on. That is how the internet works today. When a router gets a packet, it tries to forward the packet to its best destination. It makes a guess on the general direction. Hey, the packet is supposed to go that way. I get the packet here, I pass it that way. So it's what we call best effort routing. Just a sec. All right, sorry about that. So routers basically pass that packet or the hot potato to its intended destination. Now, is the router always sure that it will get to its destination? No. Are you sure that the packet will get to its destination? No. But since every router in the internet is designed to pass the packet into the general direction in which it's supposed to go, then you will normally, it will kind of get to its destination, right? So that's how IP routing works. You trust that everybody in the internet has the best interest to pass the packet, or in this case, the hot potato, to its intended destination, right? So you don't care whether it actually gets there, but so you just send it in the right general direction, okay? Now, a routing table is basically a piece of it's a data structure within a router that allows you to say, oh, if it goes to that network, send it to that router. Especially if a router is connected to multiple routers, you want to be able to send it to the right router. By default, when you buy a router and you plug it in, it has an empty routing table, right? So the routing table is actually propagated in many ways. Either you manually configure it, which is this particular lecture set, which we call static routing. So you set it yourself. or it is propagated using what is called a dynamic routing protocol, right? So routing table is normally filled with routing entries, and normally there is a specific route or a special route called the default route, which basically means if you don't know where to send the packet, just send it here. So most of us, for example, yung router nyo sa bahay, your Wi-Fi router or your broadband router will have a default route actually that just says if they don't know where to send the packet, you send it to your ISP, right? Which is, I think, reasonable if you only have one ISP. But if you have two service providers, then it becomes a little more challenging, right? So again, the routing table is where it has the entry on. If it wants to go to this network, send it to this router, right? So some general tips. So this is generally the step-by-step procedure on how to define routing. Again, there is a YouTube video on how to define or how to do routing exercises for this class. So normally you are given a network topology, right? So there's a description. You have three networks connected to each other, A connected to B connected to C, and C connected to the internet, right? So you're normally given a topology. The first thing you should do is, of course, identify all the subnets first. Make sure that you have all the networks. So A connected to B connected to C. So you have at least network A, network B, network C. Now it says network A is connected to network B. That means there is a link between router A and router B. That link itself is actually a network as well, right? And the link between router B and C is also a network as well. So in that particular scenario, you have three A, B, and C. Then you have the link between A and B as a point-to-point network, and the link between B and C as a point-to-point network. So you need to identify all the subnets as well, right? So in that particular case, for example, if I have network A, this is harder to do without the board, C, and I have routers, right? So these networks themselves have to be connected by networks also. So you have your network A. This is one network. Network B is another network. Network C is another network. Connection between A and B is a network. Connection between B and C is another network as well. Okay? So that's the first step. You need to know what the subnetworks are. The second step is, of course, you also need to make sure that for each sub-step of the first step, for each subnet network as well, you also have to make sure that they all have network addresses, diba? All of those networks have appropriate subnets, right? And subnets can be as small as a /30. That means there's only two IP addresses. There's only two valid IP addresses there. So that's the first step. The second step is ensure that all routers have properly configured interfaces. So once all your networks have their own subnets, by default, diba, like lab exercise number 3, they don't see each other. So you have to configure routing, and that's what we're going to do in this exercise. But you have to make sure first that all the routers are connected to their proper network. So for example, router A is connected to network A and network AB, the link between A and B. And router B is connected to network B and is also connected to network AB and is also connected to network BC. And router C is connected to network C and is also connected to router BC, right? So make sure they all have their appropriate networks, and therefore you give them IP addresses. Now, you can give them any IP address within the usable range. Just pick an unused IP address. So for example, if you give router A an IP address in network AB, dapat si router B must use a different IP address. Now, you can use any address, but normally in practice, we normally use the last the addresses. So for example, 192.168.0.0/24, for example. So we normally use the last address. So the last valid address is 192.168.0.254. So it's normally the last valid IP address in that subnet that we normally give. Because the first few addresses, we will always assign to hosts within the network. And of course, the third step is to configure the routing tables for all routers, which is actually the major exercise for this particular activity. Right? So these are the general steps. And the goal is really to configure the appropriate routing table so the packets actually get to their proper destination. Okay? Questions so far? Wala naman. So let's try this particular example here. So I have a router here, and I have three other routers. Notice this router is connected to a network called your network, and we just didn't define its IP address. Then we have a router here that's connected to 10.2.0.0/16. This is connected to 10.2.10.128/25, and this is connected to 10.2.10.0/24. Now, in this particular case, how many networks do I have? I have one network, which is called your network, which router A is a member of. I have another network in which this network is connected to, another network which this network is connected to, another network that this network is connected to, and I have one network between these routers and these routers. And it can be just one network here. So I can have 1, 2, 3, 4, 5 networks, and I have the default route, which is 000, which is like throw it to the internet. So I have the internet, 1, 2, 3, 4, and 5, right? Or this can be, depends, because the drawing is not very clear here, but in this case, this can be individual networks as well if they are point to point. But the rest of the examples will be clear. But in this particular case, I have a routing table that says, oh, if the packet goes to 10.2.10.128, so where's 10.2.10.128/25? Okay, this one. So I send it to this router, 10.2.0.25. The reason why I know that this is one network is because you notice all of these IP addresses are in the same subnet, right? So that means these guys, these four things are actually in one network. If I want to send it to 10.2.10.0/24, I send it to this router here. So you notice that, right? 10.2.0.0.16, this guy. So I send it to 10.2.0.2.54. And if I don't know where to send it, that's the default route, I send it to 10.2.0.2.54 as well. So this is what a routing table looks like. And our exercise for today is basically to learn how to propagate one. Okay? But before we do that, let's just do some quick definitions now. So a static route is a route that is manually added by you or me. So a system administrator logs into the router and types in a route. If you want to go to 10.2.10.0, send it to 10.253.0.2, for example. So you specifically create the route. So manually added by a person. A dynamic route is the routers themselves talk to each other and exchange information, which we'll discuss later in the class as well. Right? So let's take this example. So this is a more valid example. In this particular example, how many networks do I have? Right? So in this particular example, it's quite clear because the subnets have already been defined for me. So I have this subnet here, which is this network that contains all these PCs here and this router here. I have this subnet as well, 10.2.10.2.30, which basically has all the PCs here and this router here. And they have another subnet 10.2.50.0/24, which includes all the computers here and this router here. And I have a network between this router and this router with this point-to-point IP address. You notice it's a /30. So the valid values of this is only 10.2.20.0.1 and 10.2.20.2. Here naman, you have another point-to-point link with valid addresses 10.2.40.1 and 10.2.40.2. In this particular example, the subnets are given to me. So step number 1 is actually partially done. Now I have to configure IP addresses as well because I don't have IP addresses yet. I just say these guys are in one network, these guys are in one network, these guys in one network, and these two are in one network, and these two are in one network. So I configure IP addresses. So I have 3 routers here. Let's just call this one A, B, and C. So for router A, I have an interface 0 that's 10.2.10.1. So 10.2.10, that means 10.2.10.1 is a valid address in this network. So I gave this, so this interface here is 10.2.10.1. And the second interface is 10.2.21, right? Which is in this network 10.2.21, right? And this host, I just gave it an IP address 10.2.10.2, for example, para hindi siya mag-conflict, right? So those are the addresses. So you can define IPs that you can use, for example, for that particular assignment. So let's try to, right, so here, So this one, we gave this host 10, 10 to 10 to, right? So by IP address siya. And the interface of this router facing 10 to network is that one. But its interface facing internal is 10 to 20.1. So since ito 10 to 20.1, this one is obviously 10 to 20.2. Oh, parang, what is that? Ah, this is weird. So let's see again. 10 to 10 to. And this one. Oh nga, no, nagtitranslate siya. Nagmamarunong siya. So anyway, but you get the gist. So this is 10. Maybe if I do that, right? 10 to 10 to. Okay, si Zoom has some, si Zoom is more intelligent than me when it comes to this. So let's just, let's just draw it. Right, so this is 10 to 10 to. Right, I'm not very good at that also. Let's type it. Maybe if I put quotes, 10 to 10 to. Mas malala to. Sige, but anyway, 10 to 10 to, this one is 10, 10 to 10, 1. This interface here is 10, 10 to 20.2, because this interface here is 10 to 20.1. Right. Then this interface here, this is in 10 to 40 network, so I can give this 1 and this guy 10 to 40.2. This interface here is in network 10 to 30.1. This computer, I can give this 10 to 30.2. This one is 10 to 50.1. And I can give this guy 10 to 50.2. So I can give them specific interfaces. So that I make sure that all the interface, so if this router is connected to 3 networks, dapat may tatlong interface siya. This router is connected to 2 networks, dapat may dalawang interface siya. This router is connected to 2 networks, dapat dalawang interface siya. Make sure that all routers have appropriate interfaces. Right? That's the first step. And that's what this thing does. I simply define the interfaces. So router B, tatlong interface, therefore, tatlong IP address. Router A, dalawang interface, dalawang IP address. Router C, dalawang interface, dalawang IP address. Okay, so that's done with first step, right? I make sure that they all have subnets and they all have interfaces. The next is I define what is called a routing table entry. So now if I look at this network here, I said, I want to go, if a packet gets to router A and say wants to go to this network, I send it to this router. If it wants to go to this network, I send it to this router pa rin kasi this router A has no connection to router C. So if router A wants to go to network B, send it to router B. If a packet in router A wants to go to network C, send it to router B pa rin. So dapat yung destination niya, whether this 10 to 30 or 10 to 50, I should send it to 10 to 20.2, which is basically the interface between router A and B that's in the same network. So I know na itong IP address dito is 10 to 20.2. So that's the reason why I add that entry. In order to go to 10 to 30.0 or 10 to 50.0, I send it to 10 to 20.2, right? Now for router B naman, mas flexible kasi I'm in the middle. If I want to go to network A, I send it to router A. If I want to go to network C, I send it to router C. So network A is 10 to 10.0/24. Therefore, I send it to this IP address here, the IP address between these two networks that this router can see, which is 10.2.20.1. Here naman, I send it to 10.2.20.2, which is the IP address that this router can see of this router when I go to 10.2.50.0. That's the reason why you have two entries here, 10.2.10.0 to 10.2.20.1 and 10.2.50.0 to 10.2.40.2. So that is the IP address at the other side, right? Because this is me, I need to send it to the other side. Now, if I'm router C, whether I go to network A or network B, I simply send it to router B. But this time, I use the network between router B and C, which is 10.2.40.1. So this IP address here is 10.2.40.1. This is 10.2.40.2, diba? As we saw kanina. This is 10.2.40.1. So whether I go here or here, send it to 10.2.40.1, right? So whether I go to 10.2.10.0 or 10.2.10.30/24, I send it to 10.2.40.1. And that's it. And my routing exercise is over. And this is the routing table. Now, this is a very simple exercise, but people get tripped up because they get confused with the IP addresses assigned, and that's the reason why you should watch out for that. Right now, this is just another example. So this is a generic way of defining an IP route. Most router software will use the syntax like IAP routing, BSD, and the like. But in other operating systems, they look different. So in Linux, it looks like this: route add, the dash network address, network mask, then specify the gateways, basically the route you want to send it to. In iOS, it's similar to the syntax I have above, except that when you want to remove the route, just say no IP route, right? And show IP route will give you the current contents of the routing table, right? Then, for example, in Windows, which is what you're going to be using, sorry, you're not going to be using this because we don't have a physical lab exercise pala for lab exercise number 4. But it's okay. But if you get the chance, if you want to try it out with a physical network, you can use this in your Windows machine. But for our class, we're going to be using a Linux machine. Actually, as a matter of fact, we're going to be using Mininet, right? And for any other Unix, it looks like this. So this is how a routing table is defined, and that's it, right? So static routing issues, you cannot possibly know all routers, and that's why we created something called a default route. Kasi hindi mo naman pwede ma-define lahat ng router, lahat ng network sa internet. And that's why, for example, for you, your home network, when it goes to the internet, you just set a default route. And the destination network for default route is by default 0.0.0.0, right? Then, of course, sometimes your network is very big, and that's why there is something called dynamic routing, right? So, quick definition, the default route is something you set. In case you don't know where to send the packet, you send it to the default route, right? So, it's normally set mostly in terminals, right? So, your computer at home or your ISP routers will normally have just default routes. So, for example, your PC, by default, when it connects to a Wi-Fi hotspot, yung default route niya is your Wi-Fi router. Kasi there's no point. Anywhere the packet wants to go, just send it to the wireless router. The wireless router will send it to the internet. Okay? So this is an example of how a default route is defined. So normally it's IP route 0.0.0.0, then send it to a particular host. Right? So in this particular case, since router A has no choice but to send it to router B, just say no matter what the destination is, you send it to router B na. The same thing for router C, but no matter where the destination is, you need to send it to router B. So you send it to router B here. It's only router B that actually has a distinction, because if you want to send it to router A, network A, send it to router A, network C, send it to router C. Okay? So again, step-by-step recap. Whenever you want to define a route, and you can watch the video for this, and I'll give one example later, you basically have to determine all the networks that are needed first. Please note, even the peer-to-peer networks between routers are actually networks by themselves. And you have to have in interfaces. So in this particular case, kahit yung network na to, between routers A and B, is actually a network by itself. And this network between router B and C is also a network by itself. Okay, so that's the first step. The second step is ensure you have enough subnetworks to allocate to each of the networks. So if you're given one big IP block, you have to break it down. You have to remember our subnetting exercise, and you have to break it down into smaller subnets, right? And of course, you have to provide the necessary subnet, gateway address, and default router if necessary, if you have an ISP connection, which we'll show in the example. And of course, you have to assign subnets to the networks needed, and all of them have to have interfaces. And last step is basically fill up the routing table. Okay, so let's go to, let's cover one example on this exercise. So let's do this. Okay, do you see a notepad? Yes, okay.
Yes.
So let's look at this example here. Given two networks, network A and B. So let's keep it simple. We only have two networks connected to each other via a point-to-point network link with networks A router connected to the ISP and a non-routable address range of 10, 10, 0, 0/16 and a connection to the ISP with gateway address 202.100.200.1/30. Define the routing table for both routers A and B. So first, let's determine the topology. So you have network A connected to a router A, which is connected also to a router B, which is connected to your network B, right? At the same time, you have your router A also connected to your internet. Okay, so this is what your network looks like. So topology-wise, you have network A connected to router A connected to router B connected to network B, and router A connected to your internet or your ISP. Let's call this ISP. Okay, so question so far before I proceed. Okay, so given these words, I was able to deduce that this is the topology, right? Next step is how many networks do I have? So I have obviously network A, right? I also have network B. I have the ISP network, and I have the network between A and B. So the network between A and B is the point-to-point network between A and B. Kasi yun nga, you see this. So this is your first network, where network A is, including router A. Network B is, including router B. I have this network, the point-to-point link. So again, point-to-point links are also networks by themselves. So router A and router B are connected via a point-to-point link. That is also a network in itself. And of course, the network of the ISP, which includes router A, is also your third network. Now that means I have the ISP network has a network address by default. Since I know my ISP router, right? So I have this network already for my ISP network. Now these three don't have subnets yet, right? So I need to divide this one into how many. So I am given to divide into three, right? Since I can't divide into three, I'll just divide them into four and do my normal subnetting exercise. So to divide into four, so I hope you still remember your subnetting exercise last week. So 10.10.0.0/16. You can divide it into four by breaking it down into slash. So add 1 to the prefix length divides it into 2. So dapat /18. Okay. Right, so divide it into 4. Then since it is the fourth, so 18 is between in this case 16, 17, 18. That is the third byte boundary. So this is between 24 and 16. Therefore, it's the third byte boundary. So the third number changes. Right. So it looks like that. Then the first one is always 0. Then I have to add, right? I have to add 2 to the, so 2 to the 32 minus, 2 to the max of the byte boundary minus the prefix length. So that is 2. So I add here. Let's put it na lang para visualize. I have to add 2 to the power of byte boundary max minus 18. Right? So I have to add that in every step. So that's how I subnet, right? So let's go and let's perform that subnet. So 24 minus 18 is 6. 2 to the 6 is 2 to the 6. 2 to 6 is 64, right? So this is 64. So I 0, 64, 1 to 8, and 1 and 2. Okay, so I divided this network into 4 smaller networks. And now I can assign them. So my exercise here, I can now assign them. Let's just assign them sequentially. Medyo sayang kasi malaki yung /18, but this is just an academic exercise. Okay lang. Okay, then that's 1 to 8. That's 0/18. Okay, so step number 1 finished. Have I defined all my networks? Have I defined all my subnets and given them all IP address subnets? Yes. Now I have to give all the routers IP addresses. So how many routers do I have? I have router A, I have router B. Now router A has 2 networks. Router A is connected to network A. 3 networks connected to network AB and is connected to the ISP network. While router B is connected to network B and connected to network AB. Okay, so let's recap. Our router A here is connected to network A and connected to this network between router A and B and is connected to your ISP. While router B is connected to this network between the two, which we call network AB, connected to network B as well, and that's it. So I have to give it IP addresses. So let's try to follow our convention by using the last IP address. So network A, I can do 254, right, which is the last of this particular subnet here, the last usable IP address of the subnet here. Network AB, 10, 10, 128.254, which is the last available IP address in the subnet, right? So I assigned it to. And ISP, I have no choice because my ISP router is already .1, so I can only be .2. Kasi yun lang yung usable in this IP address here. Since given na yung IP address ni ISP, which is .1, we should be the next one already, which is .2. Okay, so lahat ng interfaces ni router A, all the interfaces of router A already have an IP address. Now I move to router B. So I want to give them IP addresses as well. So in network B, I need to give the last IP address here. So I can use 10, 10, 64, 254. It's the last. And network AB, I use the last IP address here, 10, 10, 128.0, 10, 128. So can I still use 254? I can't kasi ginagamit na ni router A. So I use 253. Okay, I hope that was clear. Question so far? Okay, wala pa. Good, good. Right. So after this step, I now have all my interfaces and all my routers have IP address. Now I can actually configure a routing table. So let's create a routing table for router A. So routing table for router A and routing table for router B. So I need to define all destination networks. So what are my destination networks for router A? So this is router A. Router A can go to network A, network B, and the default route, which is the ISP. So what is network A? So network A is this. So wants to go to network A, wants to go to network B, and wants to go to the default route. Siyempre, all packets in router B also want to go to network A, network B, and the default route. So you define that. For every router, they need to be able to reach each other. Therefore, define all the possible networks you will go to. Now, you will ask me, sir, bakit hindi kasama si network AB, si 10, 10.128.0/18. The reason why we normally don't include that is because hosts in these networks don't really need to go to the network between the two, because there are only these two routers here, in which these two routers are part of these networks naman. So you normally don't route, you don't need to put in the routing table the peer-to-peer networks. But if you do put it and you do configure a default route, it actually does not hurt. Okay. So this is my destination network, and of course the format of a routing table is destination network, tapos router, right? So what is the router you send to? If I am in router A and I want to go to 10.10.0.0.1.18, so if I'm router A and I want to go to network A, where do I send the packet? Okay, since router A belongs to network A, the convention is I put my own IP address. So what is router A's IP address in network A? That's this one. Right? So this tells me that, oh, I'm connected to that network. So I don't need to send it to another router. I'm already in that network. Right? The next one is I want to go to 10.10.64.0. So from router A, I want to go to 10.10.64.0, which is this. So where do I send it? To router B. Right? So I need to send it from router A to router B. Now I look at router B. So I need to, how am I connected to router B? So router A is connected to router B through network AB. That means I have to send it to the IP address of router B in network AB, which is router B in network AB, which is this. Right? Because I can only send it to an address that I am actually connected to. So kung ako si router A, I'm only connected to A and AB. And B is connected to AB also, so I have to use this address here. And of course, default route, if I don't know where to send it, I send it to the internet, which is my ISP address, which was given as 202.100.200.1. Okay? So I'm finished with router A. Now I move to router B. So router B, same thing. I am in router B right now. I want to go to 10.10.00/18. So 10.10.00/18 is this. So I need to send it to router A. So I need to send it to router A via the interface that router B is common with router A. So router A and B have network AB as common interface. I send it to the IP address of router A in that common interface, which is 10.10.128.254. Okay. Then if I want to send from router B to network B, since I am directly connected, router B is connected to router network B, I just put my own IP address there. And default route, if I don't know where to send the packet, I'm in router B. I don't know where to send the packet. I need to get it to the ISP. So I need to pass it to network A. So what is the interface between me, router B, and network A is network AB. The IP address of router A and network AB is this. So pass it on. And that ends the exercise for statically defining a routing table. So if you notice, in summary, you start out with defining a topology, right? Define what are your appropriate subnets. So I have 3 of them. Define what IP addresses you have. So this one, subnets, I have this one as a given, right? So this one, I just got the network address of this. That's actually this thing here. And I hope you still remember how to complete that. Then for network AB and AB, I need to divide them amongst this one kasi ito yung given. So I divided them into 4 kasi I can't divide it into 3. This is how I subnet this network into 4. I assign them. I assign the IP addresses to all the routers. Then I define the routing table. Okay? So that's it for routing. It's a fairly straightforward exercise. Again, there's a YouTube video on this also in case you need to review that. Okay, questions so far? So let us go back. Right. Do you see the slides now?
Yes.
Yes, all right. So these are some example routing exercise if you have free time. So 2 branch networks connected to 1 main branch connected to the internet. This was the example I gave a while ago. So the example we went through is an example of this. I have 2 networks, 2 routers, the 2 routers connected to each other, and 1 router connected to the internet. Then there's another example. It can be a 3-branch networks with 2 main branches connected to the internet. That means you have 2 default routes. Or a 2-tier network is an example of 2 networks with with 1 router connected to both networks. So these are some examples that you can go through if you want. But the one we went through is an example of this one, the first one. Okay. So if there are no questions on static routing, we will move towards a more advanced example, which is basically your dynamic routing. Okay, so what we did a while ago was we basically configured the routing table ourselves. We set all the IP addresses ourselves, we defined the subnet ourselves, and we defined the routing table ourselves. So manually natin kinonfigure lahat ng routing tables, right? But of course, technology has advanced sufficiently that you don't really have to do static routing, especially if your networks are very big. Now, for you and me and our home networks, usually naka-statically route yan eh. Like the routing addresses in our machines are configured via DHCP. It's still automatic, but somebody had to set that. So your ISP administrator was the one who set that, or the one who set up your home Wi-Fi. But in default, you don't really need to do dynamic routing. However, if you work for an ISP, you work for PLDT or Globe or some global ISP like AT&T, you need to do dynamic routing. So this is this topic right now. So this is an advanced networking topic called advanced IP routing. So this is a short recap of what routing was. We don't have to recap because 2 weeks consolidated into one lecture. So this is static routing we identified. Now dynamic routing, you notice the difference between static routing and dynamic routing. In static routing, you identify the subnets, you identify the networks, you set the subnet, you set the IP addresses, and you configure the routing table yourself. Dynamic routing, the first 2 steps are the same. But the third step, the routers will talk to each other and exchange the routing tables by themselves, right? So that is the difference between static routing, which you set yourself, and dynamic routing, which the routers talk to each other and set it themselves, right? Which is nice because it's all automatic. So there are 2 major classes of dynamic routing protocols. One is called interior routing protocols. This is for routing within a single administrative domain. So this is a network within one administrative control. So for example, the Ateneo de Manila University is part of one administrative network because the network administrators of Ateneo control every element in the Ateneo network. So for example, whether you're talking about the Loyola Heights campus or the Rockwell campus or the Ortigas campus, it is administered by one administrator and it's managed as one. So anything between the routers inside Ateneo, if we wanted to use dynamic routing, we would use an interior routing protocol. Although in Ateneo, we use static routing because the network is relatively simple. But whenever we talk to other entities outside, like Ateneo wants to talk to the internet or via its service providers like PLDT, DICT, and who's the third provider? Converge, for example. So we need to use an exterior routing protocol because we cannot configure their routers, number 1. Number 2 is we cannot know all possible networks in the internet to create static routes for them. That's why we use exterior routing protocols, right? So if it's in one administrative domain, it's called interior routing. So all the routers inside Ateneo, for example, we can use an interior routing protocol. But if the Ateneo router needs to talk to the Converge router, PLDT router, Globe router, that is an exterior routing protocol. Okay, so let's talk about interior routing protocols first because they are relatively simple, right? So interior routing protocols, before we talk about interior routing protocols, let's just get a few terms out of the way. If you are under one administrative control or one administrative unit, you are called, in networking speak, you're actually part of what we call an autonomous system or an AS, right? So Ateneo de Manila University is part of an autonomous system, and the Ateneo de Manila University has an autonomous system number that is unique in the entire world. So Ateneo's AS number is actually 18888, so 18188, for example. So it's not very hard to remember. It's actually quite easy to remember. So the autonomous system number basically is a unique 16-bit number. Now it's a 32-bit number, but when Ateneo got its number, it was still 16-bit, and it is unique in the entire world. The ASNs in the Philippines are assigned by a governing body called APNIC, right, or the Asia Pacific Network Information Center. Different parts of the world get assigned their addresses and numbers, ASN numbers, by different entities. So in the States, there's an organization called ARIN, and in Latin America, there's LACNIC, and in Europe, there's RIPE. Right? So here in the Asia Pacific, we are under what is called 18. So our AS number, for example, in Ateneo is 18188. Right? So interior routing protocols. There are two major classes of interior routing protocols. There's what we call distance vector routing protocols, which is the most simple and still the most effective. And there's what we call link state routing, right? So distance vector protocols are fairly straightforward. It measures the distance between routers as hops. So if it passes two routers, router 1 passes router 2, gets to router 3, that is 2 hops, right? It had to pass to 2 routers to get to its destination. Versus if it passed through 5 routers, that's called 5 hops. So the distance is the number of hops. The shorter the number of hops, the more preferred the path is. So the nice thing about dynamic routing protocols is even though there are multiple paths and loops around your network, the distance vector routing protocol will select or will add to the routing table the shortest. It will choose the hop that will get, it will choose the destination router based on the shortest number of hops, right? So that's why it's called distance vector, because the shorter the hops, the more likely it is to be chosen by your routing algorithm. And the most common types of protocols to support distance vector routing is RIP, or Routing Information Protocol, IGRP, and EIGRP. Si RIP is dead already, so kaya rest in peace protocol din tawag namin dyan because it does not exist anymore. But it is it's still here for academic purposes. Okay, so let's describe a few terms, right? So distance vector routing, we have hop count. This is the number of routers that a packet has to traverse, right? A routing loop is basically when routers keep on passing the packets, but the packets never get to its destination. So one of the problems kasi with the internet is since there can be potentially many loops, right? The only way to solve that problem, and that causes a problem which we call counting to infinity, where the packets get passed around the network and never get to its destination. So in order to solve that problem, what we do is we actually configure something called a time to live. Remember time to live when we discussed ICMP last week, right? So time to live is basically a setting that is put per packet. It's 30 by default. Every time it passes a router, that time to live number, that 30 is subtracted by 1. So it passes one router, naging 29, passes second router, naging 28, until it gets to its destination. But if it never gets to its destination, it keeps on subtracting by 1 until it becomes 0 and the packet is dropped. So that is how we avoid counting to infinity by setting something called a time to live. Now for distance vector routing protocols, para wala tayong route loops and counting to infinity, they normally set it to some small value. So for example, in RIP, the maximum is 15. For IGRP, the maximum is 255. When RIP was created, kasi maliit lang yung internet. But now that the internet has gotten a lot larger, that's why the hops have increased. However, for example, your trace route by default will drop the packet after 30. So you can technically, we have like 30 degrees of separation maximum between any computer in the internet, actually. Okay, so in this particular case, this is an example of how distance vector routing works, right? In this scenario here, you can have, this is what the subnet costs look like. So for example, from subnet 4, I want to go to subnet 1, then we have a cost here. So cost 3, subnet 2, right? If it's via 2, it's subnet 2. So you can choose the cost depending on what you like. So for example, here, I select network C, because in order to get to subnet 1, it is equally costly to pass through network C or network A, right, to get to subnet 1. So to get to subnet 1, here, I can either pass C or A. But the distance between A to B, which where subnet 1 is A, C, B, right? Let's say, so 3 routers, or A, D, A, B, which is also 3 routers, since they're the same. So I just pick C. But in order to get from, say, subnet 3 to subnet 4, right, subnet 3 to subnet 4 here, I can have 2 hops, D and A, or I can 4 hops, D, C, B, A. So syempre, it picked the shorter one, which is 2 hops, right? So that's how distance vector routing protocols work. It chooses the route, it creates this routing table entry based on the shortest or the smallest cost, okay? How it works, and let's talk about a specific protocol. So the first one and the oldest one is called the Routing Information Protocol, or RIP. So RIP is the oldest protocol in the dynamic routing protocol family, defined by RFC 1053, 58, and 1723. 1723 is RIP version 2, and 1058 is RIP version 1. So packets are done using packet update. So the routers update themselves, so they talk to each other. So you just have to define your individual networks, define what network the router is connected to, and just point to the neighboring routers, right? So it's as easy as that. So this is how you configure it. So in Cisco, because you normally don't do dynamic routing in your laptop, for example, or your desktop, you normally do it in ISP routers, right? So for example, a Cisco router, and similar syntax to all other routers like a Juniper Extreme router. In this particular case, you just type route rip, define the network you are connected to. So this is the network you are connected to. So my network is 10.2.0.0. You can also set a mask, by the way. If there's no mask, by default, it assumes it's /16. And set the neighbor. So you type neighbor and the IP address of your neighboring router. So for example, in a RIP configuration, let's look at this example here. I have 3 routers here. This one is connected to 192.168.0.0/26. This is 0.128.26, 0.64.26, and the network in between is 0.192.26. So this one, I took the step already of defining that I have 4 networks here, 1, 2, 3, and in the middle 4, right? And they're all connected to each other. And I defined subnet addresses already for each. The next step is I will configure IP addresses for each, right? So in this particular case, then 00, I put this interface here is 01. Here, this interface here is 65. This interface here is 129. That's 128, 129. This interface here is 0194. Oh, there's a typo here. So 193. I think this is 195. Yeah, 195. Ayusin natin. Baka future generations ma-confuse. So that's 195. Right. So here is 193, 194, 195. Now, in order to configure RIP, I don't need to define a routing table na if destination is all of these and I send it to each other. So I don't have to do that anymore. I simply configure route RIP, define my network. So for router A, I am in 192.168.0.0/26, and my neighbors are these 2 guys here, 194 and 195. And I configure router B, my network that I'm connected to is 192.168.0.1.2.64 in case, and I /2026. And my neighbor is, for example, in this case, I only specified router A. And in router C, my neighbor is only router A, right? And they will exchange packets by themselves. Okay, so may typo din to router. Okay, so that's it for RIP. That's how you configure RIP. And now, as a matter of fact, this syntax applies to any dynamic routing protocol. You simply define the protocol, your network, and your neighbors. Now, is it okay, for example, for router B, I also define 192.168.0.195 as a neighbor? That's actually fine, right? So that's actually something that you can do also. You can do this. So 195. That's possible as well because this is connected to both of this. And this one, I can also add 194 here. Right, so those are options you have for your routing table. Okay, so that's it. So RIP is, if you notice, it's very easy. You don't have to define all your destinations and define your default your routers for all of them, and you have to define 3 routing tables. Just configure RIP, my network, and the neighbors. Right? IGRP works in the same way as RIP. except that it has a bigger hop count kasi 15 they realize is too small kasi ang laki na ng internet. So the hop count became 255. IGRP also has the flexibility to work in internal, external systems, which makes it also good. And although it's Cisco proprietary, so it only works for Cisco equipment, right? If you notice, the syntax is the same, except that you just have a number here. This number is an AS number. So in Ateneo, it's 18188. If you want to set one, you have to apply a number from 1888. The reason why it allows the definition of an AS number is because it can be used for exterior routing as well, although it is not used today for exterior routing, right? And you have extended IGRP. So again, the syntax is the same: route, neighbor, route, network, neighbor. That's it. EIGRP is just an extended version of this protocol, right? And this is how the syntax works. So again, it's similar. You notice, except that I added the AS number here, right? And this slide also has the problems of the previous slide. So, okay. So EIGRP and RIP have the same. EIGRP, IGRP, and EIGRP and RIP all have the same syntax. Define route, neighbor, route, network, neighbor. And you can have as many neighbors depending on the routers you are directly connected to. Right, that is it for distance vector routing. The second type of interior routing protocol is what we call link state routing, also known as shortest path first routing. So instead of just using hop counts, it also uses other pieces of information like congestion and bandwidth. Now, of course, you can already see the trade-off between distance vector and link state. In distance vector, it just simply counts the hop. Whether dial-up link lang yung between the shortest route and broadband yung ibang route, distance vector routing protocols don't care. It will always pick the shortest route, even if though that route is short. Now, in link state routing, it takes advantage of information such as congestion and bandwidth. So it actually keeps and exchanges information on congestion so that it can avoid congested networks. Link state routing is actually the most popular type of interior routing protocols used by major networks because it's intelligent enough to actually know that a path is congested. While distance vector kasi distance, yung number of hops lang, it doesn't care about congestion. Now, the drawback with this type of network, na link state, is it of course needs more processing power. Diba? Kasi as you compute more factors in not just hops, but bandwidth and congestion information, syempre mas mabagal to select a better route. That one is what we call convergence time. And that's one of the drawbacks with link state routing. So how does link state routing work? You consolidate all the network information. So all routers talk to each other and broadcast what we call link state packets. So link state packets are sent to every router within your network. So medyo that part pa lang, medyo matrabaho na yan kasi instead of just hop count, you also have to send congestion information and bandwidth information, which you have to update more often. Kasi in distance vector, you only exchange router updates when you have a topology change, right? When a link goes down, etc. But in link state, since you have to exchange congestion information, you have to exchange LSPs all the time, right? Then it builds a routing table, factoring all the information from the LSPs using the shortest path first algorithm. So mga ComSci majors here, you have to remember your Dijkstra's algorithm, which is the one that's basically used here, okay? Then the routing table is recalculated based on every new LSP. So when a new LSP comes in, it recalculates. Now, there is a gap between my old routing table and my new routing table. Again, I mentioned a while ago, that is what we call convergence time. So every time a route changes, it takes time to converge. When a link goes down, it takes time to converge. Unlike distance vector, since a link goes down, that's an absolute topology change, that link is simply avoided. So mas mabilis yung convergence time with distance vector protocols. As opposed to link state routing protocols, there's a lot of computation that has to be done. That is the reason why the trade-off here is really power, memory, and bandwidth. But you get more efficient routing, diba? But for internal routing protocols, kasi that's okay because you control all the routers in your network, you can make sure that they have the appropriate amount of power, memory, and bandwidth. Okay? So that's it for interior routing protocols. This is just a visualization of link state updates. OSPF pala is the name of the actual protocol for link state routing. It is the most popular one. There are many, but this is the one that's actually used right now. And these are the benefits. Again, no limitation on hop count, fast convergence time, and it is aware of network delays and link costs, so which is quite useful, right? But the cost is specified in the administrator. So how I configure it, you have an additional number here. It's called the process ID, right? So this is just a way to divide your internal network into smaller networks, even if you create them as as part of one OSPF zone. Then you define your network address, meaning what network you are directly connected to, and you can specify OSPF areas as well. So you can divide your network into smaller processes, right? And each of your processes is part of like one big campus, for example. And within the campus, you can actually create an area. What happens kasi is OSPF will prefer updates or react to updates within an area more than updates within a process. Okay? Then you can specify or hard code a cost. For example, DSL yung link, you put a cost 5. Fiber yung link, you put a cost, for example, 10. Or if it's a dial-up, you put a cost 1. There you can specify priority then. If two links have the same size, they're both fiber, for example, but you want to prioritize one, you can specify a priority, right? And this is just to get the information. So in our example a while ago, if I configured it using OSPF, you notice, again, same pa rin siya. Except that instead of EIGRP, I just use OSPF. And in the case of my process ID, I just use my AS number. And I define the same thing. Everything else is the same, except that I now specify an area, which is optional, by the way, because I can treat this as one part of the network, another part of my network, and another part of my network. Okay? So that is it for open link state routing protocols such as OSPF. So notice, all of them have a familiar syntax. Router, to define the protocol. Network, to define the networks that are connected to me. By the way, can be more than one. And neighbors that are directly reachable by me, that can be more than one also. Okay, questions on the interior routing protocols? Okay. Right, so let's move on to exterior routing protocols. All right. So there are two major types of interior. Okay, so exterior routing protocols, there's only distance vector. Walang link state versus distance vector. They're really just distance vector, but they have what is called policies, right? Which I will display in a while. So there are two main common types. There's EGP, or Exterior Gateway Protocol, and BGP, which is what is used today, or Boundary Gateway Protocol. So the most popular dynamic routing protocol in the world today is BGP. As a matter of fact, this is a mainstay in any networking exam, especially the more higher level certification exams, is BGP configuration, which we will be learning in the class today. Right? So EGP is an exterior routing protocol that is distance vector also, right? It is actually similar to RIP. So you can think of RIP, but used for routers that you do not control. Now the problem lang is it's prone to routing loops because, again, since you don't control all the routers, the updates can be filtered, for example. So it can be, and of course the time to lives can also be increased, right? So it is a possibility that route loops are created, and this is the reason why EGP is no longer in common use today. Right? Also, it's quite noisy because you have to poll the neighbors quite often, and that's the reason why you have a lot of inter-AS messages. Right? That's the reason why they moved on. The internet didn't stay with EGP for very long because they were just trying to use RIP for external routing, which didn't quite work out. So they created a more advanced protocol called BGP, or Boundary Gateway Protocol. It is an inter-AS protocol. That means you connect this to networks that you do not unnecessarily administratively control. It's a TCP protocol running on port 179. So TCP 179, this is how routers talk to each other. It's currently at version 4 and has been at version 4 for more than 20 years. That's how stable the protocol is, right? And it has the ability to determine routing loops and to define policies as well. That's the reason why administrators can set preferences. You can determine what network you prefer or not, right? The basic policy tools for BGP, these are just a few of them. There are actually plenty. The basic tools is what we call prefix lists, means you can define routes. So for example, I am at Ateneo, I'm connected to VICT, PLDT, and Converge. but I want traffic from Ateneo to the ISPs to move in and out, but I don't want traffic, say, from one ISP to go to another ISP. Diba? Kasi that doesn't make sense to me kasi I'm paying it for internet. I don't want a Converge subscriber to use Ateneo's network to access PLDT, right? So you have to create prefix links lists for that. And that's the, you can define, okay, networks within my network can go in and out, but if it's from somebody else within outside of this and somebody else outside of this, cannot go in and out. So that's a prefix link. You can also filter like certain directions. Okay, traffic from this network to that network can only go inbound or outbound, and you can filter it instead of by route, you can filter it by AS numbers. I don't want to deal with this for particular ASs. And you can use route maps to create policies. Like in this case, the advanced tools are local preference. You can set a weight. You can make a link more expensive than another link, which is similar to OSPF. You can also do AS path prepend. This is a way of making an AS or a particular ISP not preferred. And you can use BGP communities. The example I'll show later uses prefix length and AS path prepend. You can configure BGP, again, same, router, network, neighbor. Configure router BGP, set your AS number, the same as all the other dynamic routing protocols. Define the network that is directly connected to you, like all the other routing protocols, except that there's no area here, unlike OSPF. Then you set your neighbor. The additional syntax here is your neighbor is obviously from a different network. That's why you have to put the AS number of that neighbor as well, in addition to the IP address of the router, your peer router in that neighbor, right? So this one actually connects ASNs together, right? So me and my ISPs, I define the ISP router as a neighbor. Then this is just to debug and troubleshoot. Right. So BGP, when will you use BGP? So by default, you and I, well, not I, but you guys will never need to use BGP under normal circumstances. Unless, again, you work for an external service provider, like a PLDT, Globe, Converge, etc. You have to learn this, there's no choice. Or two is you want to do something called multi-homing, meaning you are a big organization and you want to have multiple service providers and you want to use all of those service providers at the same time. Unlike, for example, your home routers where you use protocols like VRRP to load balance, this one, those protocols cannot use both providers at exactly the same time. What happens is you normally use one or another. But with BGP multi-homing, you can use both ISPs at the same time. As a matter of fact, you can even load balance traffic between multiple ISPs. And that is the #1 use case for BGP. That's why organizations like Ateneo, for example, has a BGP number, LASAT has a BGP number, etc. Because we are organizations with large bandwidth requirements. And that's why we have to buy bandwidth from multiple providers. Now, the second reason is because if you want to connect to the outside world and you have multiple providers, you can't memorize all the routes and type them in your routing table. Masyado namang marami yan. It's impossible to statically define. And you cannot expect EGP routers to talk to all of them. As a matter of fact, there are more than 120,000 routes in the internet already. I presume the number has doubled already since the time we wrote that in, right? But of course, an ASN number is required to use BGP because it is only for inter-AS communications. So this is an example of BGP. So this is so I have 3 AS here. So AS10 is my ISP1, AS20 is my ISP2, and AS30 is myself. This is my router connected to 2 ISPs, and I have 2 networks, right? Actually, 3 general networks inside. I have network 10.1.1.1.0, 10.1.2.0, and I have a server in 10.1.2.1.30, right? So these are 3 different networks, and I want, for example, that I want to configure BGP in such a way that traffic from ISP1 is only usable by this network, and traffic from ISP2 is only usable by this network. So those are things you can do with BGP. You can what we call multi-home. Okay. Other reasons or other definitions of multi-homing is you have multiple links to the same ISP, right? You have multiple big amounts of bandwidth connected to the same ISP. Multiple links to different ISPs, the most common use case. You have multiple links to the same ISP as backup links. And you can load share between primary, secondary links, or you can differentiate like the slide I showed a while ago, where you can select traffic to go from one ISP or another. For that example a while ago, so you can use, for example, in multiple links, same provider. This is router A facing one router and router B, router A facing two routers. These are the same examples. So multiple links, same provider. So ako, si 18.18.8, my network is 10.0.0.0/24, right? So that is my network. I have a neighbor called 10.1.1.1, 10.1.1.1, and remote AS is 6163. So 6163 is the AS number of an ISP that no longer exists called Moscom, right? Which was one of our first ISPs in Ateneo. This one, eBGP multi-hop 5, just simply means that this 10.1.1.1 might not be my border router. My router might not, there may be more routers between me and that BGP router. So this simply allows that, right? And I pass the traffic all to that serial interface. So this one is one router facing one ISP. Not very useful because you can just do a default route, right? You don't have to put this all. So now this one, if I have two routers, but the same ISP, I have one router called 10.1.1.1, another router called 10.1.1.2, but they are the same AS numbers. Because that means they're the same provider, but there are multiple links, and I can set a maximum path 2. In this case, I have 2, right? Because by default, it's only one path per provider. So this one is I created 2 paths to one ISP passing through 2 different routers for redundancy. But these 2 use cases are not very common, because if you have the same service provider, you can just statically route and it's okay because it's the same service provider anyway. Now, this is the most common use case for BGP. It's multiple links and multiple providers. So ako si AES 18.18.8, and I have 2 ISPs, 6163, which is the former Moscom, and A18.18.7, which is Source Telecoms now. So that's the former Fiber City or Wi-Fi City, 18.18.7. So 18.18.7 is one of those. So there are two ISPs. I want to connect both ISPs to me. And this is my network. Internally, I have 2 networks, 10.0.0.0 and 10.0.1.0. Right? So how do I configure BGP for this? So easy. For router A, since I only have one router in this example, for router A, I define both networks, 10.0.0.0, 10.0.1.0, right? Then I configure both network neighbors. Let's just assume this is 1.1.1.1 and 2.2.2.2. So configure 1.1.1, 7.63, 1.1.1.2, 18.18.7, we'll have 5, right? That's done. It will actually work. This will actually work. But there are problems with this configuration. Number one is the network can transit, meaning traffic from Moscom can go to Wi-Fi City, and traffic from Wi-Fi City can go to Moscow, because we allow traffic in all directions. That's why we have to set a policy, right? So some of the policies, like for example, in this particular case, traffic from, if LaSalle and Ateneo are in the internet, and UP as well, I can actually get traffic in drawing that in. So what we want is traffic can go this direction and that direction, or traffic can go this direction or that direction. But because I did not set a policy that restricts it, traffic can move from, instead of here going like that to UP, traffic can go from here inside Ateneo and go to the side, which is a bad thing, right? So I don't want that to happen. Traffic goes in this direction, right? So I only want traffic in and out of Ateneo to go in. So dapat in and out lang. So I can set a policy for that, right? So that policy, you can use filtering. So meron pala akong drawing. Yan. So we can be transit provider. So this is what you add. So kanina I added, so this one we set this. We added these 2 lines up here and these 3 lines up here. So here we have a prefix list OLT out, prefix list ILT in, prefix link OLT out, ILT in. So what does that mean? First, let's look at this first 2. So ILT means like internal, right? So I permit anybody to come in. So ILT means I permit these guys, and OLT means my current network. So OLT out means anybody from my internal network can go out, and anybody from the outside can come in. And I do it for both links. Then I create a free path a prepend. So route map, as I mentioned a while ago, can be used for advanced policies like ASPath prepend. In this particular case, I give it a prepend PP, named it PP, and said for outbound traffic, I prepend 1888 twice here. That means this one becomes cheaper. Kasi this one is 1888, 6163 to destination. This one becomes 1888, 1888, 1887, then destination. So this one becomes more expensive. So by adding the prepend here in this route map PP out, this 6163 becomes cheaper, right? By doing this OLT in, allowing out to go out, allowing in to come in, that basically prevents this thing from happening. Okay? So that's how you configure multiple links and multiple providers. Notice it's not very difficult once you configure your network. And it's really a question of setting the policies that you like. And there are many, many more policies than what I'm just mentioning here. This is just an example of a filter policy and a prepend policy. Prepend policy allows you to prioritize traffic, right? Question so far for exterior routing protocol. So that's basically it for that. I mean, you don't really have to worry too much about it because there are not a lot of exercises with respect to that because you're not really expected to use it in real life unless you run an ISP. But if you do want to run an ISP in the future, you want to take a certification exam from a networking provider, you have to study this a little more. But this is the basics already for exterior and interior routing protocols. And actually, most of the time, you can this is enough material actually to pass the certification exam. Now we will discuss some other routing protocols that don't quite fit the bill between interior, and exterior routing protocols. So the first one is what we call route discovery protocols. So these are protocols used to discover routes, meaning instead of using routers to talk to each other by hand, you can actually create these protocols so that routers can determine the presence of other routers by themselves. But again, these aren't very common anymore, right? Except for IPv6, which has a router discovery protocol based on ICMP as well, similar to IRDP. This is not used in IPv4, so we don't see this a lot, okay? Now this one is this is gaining in popularity. This is what we call first hop redundancy. The thing with BGP multi-homing is you can determine policies even in the furthest reach of the internet. You can define, for example, through, you can configure BGP, like Ateneo configures BGP, and we can inform the internet that, you know what, whenever possible, send traffic through the ICT, for example. We can create that policy and we can create a parang policy request for that so that the other parties, when they send traffic to us, will prefer the ICT. Remember, majority of traffic is actually downstream versus upstream. So it doesn't matter where you send the traffic going out. What's more important is how it comes back in. So even if you send traffic out preferring one provider, but if it comes in preferring the other provider pa rin, you did not set the policy you like. But with BGP, you're able to do that. You're able to say, okay, send it out this path, but I want it in the same path. Or send it out this path, but I want it to come in the other path. You can set policies like that, which is pretty advanced actually. But first hop redundancy is in the case where, what if I'm just creating my home router and I have two ISPs connected to my home router, diba? And I can't apply for an ASN because I'm a small entity, like my house, right? Of course, APNIC will not give me an ASN even if I wanted to pay for it. So how can I do load balancing? So one of the cheap ways to doing that is what we call first hop redundancy. First hop redundancy is simply if you have more than one or two ISPs, you connect them to your router, it will simply say route traffic through one link, it comes back through that one link. Route traffic to the other link, it comes back through the other link. So it's a very crude way of routing, but it is actually good enough for yung mga home use cases natin. Unlike say ISPs kasi, you can have 5 service providers going out, but you prefer all the traffic inbound to follow certain needs or geographical basis. So mas maraming policies to set. But in your house, it doesn't really matter. You treat both ISPs equally, then you just divide the traffic between the two. If one link is bigger, then send 30% of the traffic out one. You expect 30% of the traffic back in through that ISP. That's what we call first hop redundancy. There are 3 main protocols for that, and I mentioned one already a while ago, VRRP, but I'll mention all 3 now. So hot standby router protocol is one of the earliest protocols in this space, RFC 2281, defined by Cisco Systems. So it's a proprietary protocol. It's only supported by Cisco or licensee routers. Although there are a lot of licensees of Cisco, so you can support this. It provides default gateway redundancy, but you can only have one active and one standby, meaning you can do two ISPs, but it only uses one by default. And when that one ISP goes down, it automatically shifts to the second one. Not very nice, but it is useful enough for redundancy. Now, VRRP is similar to HSRP, except that it is not proprietary, right? So that's the difference. But you can, but the nicer one is GLBP, which is Cisco proprietary, which actually allows you to load balance, meaning send 30% traffic here, 10% traffic there, or 50-50. Right? So here are some of the examples. So you can all can do load sharing, but GLBP can actually do round robin and weighted. So it's a lot more flexible, right? And the standards defined are the RFCs there. So 5798 for VRRP is just open. Problema ng sa VRRP does not support IPv6, right? And yes, that's it. Right? It uses multicast groups actually to talk to the various routers in this particular protocol. So this is first hop redundancy. Ito, you can use this in your home routers. As a matter of fact, some of the more advanced home Wi-Fi routers actually support this. You can put more than one ISP link. One of these protocols are being used. Okay, so that's it for today. Are there any questions so far on routing? So in summary, we discussed static and dynamic routing. For static routing, it's routing that you configure yourself. You fill up something called a routing table. You specify your destination networks and the routers in which to choose. The reason why that is possible is because you define the path that can be taken, or you can define multiple paths and you can set weights. But you have to define them statically. That is why it's called static routing. Now, default routes can be configured, particularly for hosts like your laptops or your ISP routers, because you only have one way out of the internet and the rest is your internal network. But of course, as networks get larger and larger, it becomes more difficult to configure it by hand. That's the reason why we have dynamic routing protocols. Dynamic routing protocols come in two types, some for internal use, some for external use, so internal routing protocols, exterior routing protocols. Most popular interior routing protocol is OSPF, and the most popular exterior routing protocol is BGP. The general syntax for defining exterior routing is simply router to specify the protocol, network to determine networks that are present within your network, and neighbor to determine your routers that are reachable directly to you. Right? But if you need to set anything such as special policies, BGP is the protocol to go because of its rich policy set. But if your network is simple, you want dynamic routing functionality like load balancing, you can use one next hop standby protocols like VRRP that basically allow you to have one hop redundancy, which is sufficient for retail use cases, right? Then for the routing configuration, the static routing configuration, the steps are, first is you have to know the topology, right? Determine the number of subnets. Make sure every subnet has a network, a subnet network assigned. Assign your routers interfaces must all have IP addresses, and only then can you configure a routing table, right? The answers to those questions in the routing table determine on the IP addresses you configure. So if you don't configure the IP addresses properly, then there is no way you can configure your routing table. If you don't subnet properly, there's no way to determine the IP addresses. Okay? Questions, guys? Excellent, right? So as I promised, this will be short. So ano na lang, so please take note, lab exercise number 4, lab exercise number 3 is due on Monday. And lab exercise number 4, you will have an assignment also that's routing related. Please review na lang the YouTube video or this video when I post it, para in case you have questions on the computations, meron kayong samples. Okay, if that's it for today, thank you very much and have a good weekend.